Hello everyone. Today we are going to be going through curve sketching, through concavity and points of inflection. Okay, so we already talked a little bit about how we discuss curve sketching through vertical asymptotes, horizontal asymptotes, critical points, increasing and decreasing values. So today we will be talking about concavity and points of inflection. Okay, so concavity. So concavity is kind of when you look at the shape of a graph, you can see when it's coming off a critical point, you can see whether the concavity of the interval is going up or if it's going down. So what do I mean by that? If I were to, let's choose a template here. Okay. So let's say if we had a specific function f of x and we are looking at concavity. Okay, so concavity is determined through the second derivative. Okay, so let's say if we have a function, right, any function, where the interval is in between points A and B in the domain, and where the slopes are increasing, okay, in which the slope is increasing. So when the slope is increasing, we can go from a negative slope to a more positive slope, right? And we can also go from a positive slope to an increasingly positive slope, right? So what do I mean by that? Let's say if we have an axis here, this is the x-axis, sorry, this is the x-axis, this is the y-axis, and let's say if we have a point here, that's A, point here, that's B, and let's say if we have a graph that's going from here to here, we have increasing concavity. So how do I know that? The reason why I would know that is if I were to put tangent lines, let's say over the graph, let's say over here, and let's say over here, then we know that it's increasing, right? The slope, so slope over here is decreasing, it's a negative slope. This slope is still negative, but it's getting closer and closer to zero, right? Getting closer to a minimum point. It could either be a local minimum, it could be an absolute minimum. We're not sure, but that's not the point of this. The point of this is just to see that the concavity, which is the rate of change of the slope, is increasing. The change in slope. That's what the double derivative means. We know that the slope is decreasing here, but now we're taking the slope of the slope. We are seeing, now we're looking at just the red lines and we're seeing how they're changing, right? It might sound a little confusing at first, but we don't have to get too deep into it. All we just need to understand is that the slope is just increasing, right? So it might sound weird because we know that the tangent is decreasing, but the change in that tangent is increasing, okay? So this is just an example where we have a function that's decreasing. We can also have this within a function that's increasing as well. Okay. So let's say if I were to draw a function, same idea, we have points A and B, we're going from left to right, and we have a function that's increasing now. Okay, let's say it's increasing that way. And if we were to draw the tangent lines again, we would see, oh, that was a bad one. We would see that it's still increasing. Oh no. We would still see that it's increasing, right? The change from this tangent to this tangent, we're increasing, right? So this is what's known as concaving or concaving. This is an upwards concavity, right? This f of x is concave up. That's what it means, right? So we're just looking at, just to highlight, we're looking at the change the rate of change of the tangents are increasing. Okay, so now that we know that the rate of change is increasing, let's look at an example where the concavity is negative, okay, or concaving down. So let's look at another function, g of x, right? In this example, we are going to concave down. So we can see here, if we were to create a graph, we can say, let's say this is for A, this is for B. Draw another function. So if we're concaving in that direction, we can see that here, the concavity, the tangents, the slope is decreasing, because here we see that we have a really high slope, and then we have a not as high of a tangent, but it's still positive, right? So let's say, for example, slope of this line could be, well, if we look at the rate of change, it's almost about -2. And then if we were to look, or sorry, +2, because we're going upwards. And the slope of this is, we see that we're increasing by 2, but we're going by 4. So here we're increasing by how many per step? We're increasing about 1, 2 per step. In this case, we're increasing by maybe 1 per step, okay, versus the 2, okay? And so this is what happens when you are concaving down. Your tangent, your rate of change of the tangent is decreasing. So we have another, we can do another example too. So in this example, we're doing y and x. Let's see if we can do another example where y and x for g of x, and let's say for 2 points, if we have a function here and we are decreasing, oh, doesn't like curves. So we have a function here that's decreasing, right? So our rate of change is still going to be decreasing. We're going from a not as negative slope to a more negative slope. And so, sorry. So we're going from a not as negative slope to a negative slope, right? So we have here, if we were to draw a tangent, we can draw here and here, all right? Well, that's a bad tangent. How about if I draw another one here to here? Oh my god, this is not working out. Right here. Okay, perfect. So we see that the rate of change between the two tangents, we see that it's decreasing, right? It's getting more and more negative. And here it's also getting more and more negative. It's going from a really positive slope to a not as positive slope, okay? Perfect. So now that we've gone through concaving down, sorry, 1 second. Concave down, right? So, and we also know that, let's say if your derivative is 0 and your double derivative will also be 0, right? So essentially when you're taking the double derivative and it's also 0, you also got to see what does that mean? If you have a double derivative that's 0, that means your concavity is not changing at all. The rate of change of the tangent is not changing. That means your tangent is probably still the same throughout the point. So that means there's no change in concavity. So let's do an example of a function. And essentially, your double derivatives can also see if you have points of inflection. Okay, so there are multiple conditions. We could also see that if your function has a critical point and the double derivative is 0, then we can see that depending on if we can see if it's a local minimum or if it's a local maximum, right, by taking the second derivative. So we have a couple scenarios. We have scenario 1, we have scenario 2, we have scenario 3. This is when you have either local minimum or maximum, okay? So what this means is when you have, let's say, a graph with concave down, the x equals c is a location of a maximum value of a function. So let's say if your derivative of x equals 0 and your double derivative is, or let's say at that point, actually here, a better example would be, let's say if we have a location x representing location of local minimum, and we have a value of that function, right? So let's say if we have a value of the function, so that's a value of a function, and so if we take the double derivative of a value, right, and it's greater than 0, then we know we have a minimum, a local minimum. Okay, so what that means is, let's say if our derivative is a local minimum and maximum, and we don't know which one of the two it is, right? So because when you take a tangent of a function and it's 0, you don't know if it's a minimum or maximum. So this is another way to determine if it's a minimum or maximum, right? You take the double derivative and see if it's positive or not. If it's positive, we know we have a minimum. If it's negative, we know we have a maximum, okay? So let's say if we have a function, or actually, no, this looks way too like a quartic function, so let's just kind of like that, right? We know since it's greater than 0, we have a local minimum. Okay, and then we also have what's called the graph that concaves down. So this is essentially concaving up because we still have a derivative, a double derivative that's positive, right? Because this can kind of clash with what's happening here, right? This is still positive. The double derivative, oh, sorry, should probably write it in black. The double derivative of this is positive. The double derivative of this, oh, sorry, is negative. It's less than 0. So this is going to essentially overlap with 1. So what's the difference? The difference here is that for step number 3, your f of x is equal to 0 with 1 derivative, because that will tell you if it's a local minimum or maximum. But the thing is, you don't know if it's a minimum or maximum. So how can you tell? You take a derivative again and you see if it's greater than 0 or not greater than 0. So this is if it's greater than 0. What if it's not greater than 0? What happens? So it's just the opposite, right? We are going to get a local maximum, right? So the graph concaves. So in this case, concave up. This is local minimum or maximum concaves down. So in this case, we see that this is going to be a maximum. This is going to be a minimum for step number 3. For step number 4, we're going to look at the maximum. it's concaving down. So if x equals c, right? So if it equals c, right? Sorry. So let's say if this equals c, so our double derivative at c is less than 0, and our derivative for the original function, or at c I guess, is equal to 0, right? So what's going to happen here? We're going to create Cartesian plane. Right? And let's say if we were to let's say this is just a rough sketch. So this is going to be local maximum. It could also be absolute, but most of the time it's only looking for local maximum because we're looking at it for each critical point, right? So this is for an example where it's less than 0, the double derivative. So it's going to be a local maximum, okay? We also have points of inflection. So there's still some other scenarios. Points of inflection. It's another topic. So what do the points of inflection do? They occur at C and F at C. So this is just saying that at an arbitrary point, at that x and the value of x, so the x and y values of y equals to f of x, if f of double prime x changes sign. So changes sign at x equals c, that means it changes. So in other words, it's changing. So changes from concave down to concave up. Oops. Or vice versa. So it can change either way. You have a point of inflection, right? So for example, what that means, that's C and FC. So let's look at a point on a graph where there's C, right? So let's say this is C, and then we'll draw like a cubic function, right? So if we were to draw a cubic, that's the best example for a point of inflection. So let's say at that point, there's a point of inflection. We're changing concavity, right? Because if we take the tangent of this, and then we take the tangent of this, it's getting less and less. So this is a concave down. But then here, it's going from here to here. So that means the slope is increasing. So that means it's going from concave down to concave up. So there's a change. So that means there's an inflection. So this is not a critical point. This is just it is still... A critical point is seen as where you're seeing changes in direction, but it's not, right? It's still changing. It's still increasing. It's not going like this, right, as we do with quadratic functions. So this is just known as an inflection point or point of inflection. Okay? So then we also have one more example. If all inflections on the graph must occur either where it equals 0 or where it's undefined, right? So let's say if all points of inflection on the graph, so all inflection points have to happen where it equals 0, where the double derivative equals 0, or if the double derivatives are undefined, right? There has to be a point of inflection on the graph. It must occur. Okay, so that's point 5. all points of inflection on the graph y equals f of x must occur either where d square y, so I'm just using Leibniz notation, d of x squared equals 0, or where d squared y over dx squared is undefined. Oops. Okay. So these steps are also in your textbook. Okay. So there's 5 steps that you need to look for when you're looking at concavity. So let's do an example. Okay. So let's say if you're given a cubic function. Okay, let's say if you're given f of x equals x cubed minus 3x squared minus 9x plus 10. Okay, let's say you want to take, so first you need to take the derivative to discover critical points, right? So first, take first derivative. Critical points. To find your critical points. Oh my god, this is really bad handwriting, sorry. Okay, so you want to figure out your critical points first, right? So you need to take the derivative and then factor, right? Equal it to 0. Okay, so you're going to take the derivative. So we have f of prime x is equal to 3x squared minus 6x minus 9. So that will be our quadratic function, right? So now we know we can factor this, right? Oh, we can actually common factor this first. So we can take the 3 out. We have x squared minus 2x minus 3, right? So you common factored it. So now we only have to worry about this quadratic. And so we have simple trinomial factorization. So we have our x and x that multiply to our x squared, right? And then we need 2 factors, basically, that will sum up when we take the horizontal multiplication to negative 2x. And then we have these 2 factors that multiply with each other to equal negative 3, right? So in this case, we can try doing negative 3 and 1, right? Because here we see that negative 3 times 1 will equal negative 3. We take these 2 and multiply them, and when we add them, we will get negative 2x. Okay? So then we could just take the butterfly, and then we will get x plus 1, x minus 3, and then we also have our common factor 3 still there, and we set this equal to 0, right? And now we look at the individual factors. 0 equals x plus 1. We're going to get x equals negative 1. 0 equals x minus 3. We will get x equals 3, right? So these will be our factors. These are the critical points. These are where you will either see an inflection point, right? Or essentially not really an inflection point, because we know that it doesn't, the tangent doesn't really equal to 0. It could. So essentially what we need to assess here is that we can see if our double derivatives can equal to 0 to find an inflection point. But these 2 values are critical values, okay? These are where we will see that we have a tangent equal to 0. So that means we have a local minimum or a maximum point, right? So now let's take our double derivative. So before I do that, I'm going to say set equal, and then for 3, find roots. These are the roots because roots are the values of x when y is equal to 0, right? So now let's take the double derivative, right? So we're going to do the d squared y over dx squared. And if we're taking the double derivative, we're taking the derivative of this, right? So if we're taking the derivative of this, we're going to get 6x minus 6, okay? Getting 6x minus 6. So now we can set this equal to 0, right? So, oh, sorry, not 3, 4. Take second and set it equal to okay, so we're going to set it equal to 0, so 0 equals 6x minus 6. So then we're bringing the 6 to the other side. We're going to get x equals 1, right? If you want me to show it, it's just right, and then x equals 1. Okay, so now that we know that x equals 1, we know that we have, oops, sorry, this is from a previous class. Now that we know that we have an inflection point at that point, right? So we have our two critical values, we have our inflection point. So this is inflection point. Oops. These are the critical values. So now we're going to determine the concavity between them, right? So we're looking at the interval, right? We're going to see, so we're looking at, we have a couple of values, right? So we have it at x equals 1, we have at x is equal to -1, and then we also have x equals 3, right? Now, the thing is, we have one inflection point, so we need to figure out what's happening around that inflection point. Like, is it concaving down to up, or is it up to down? So to do that, we look at the interval between them. So x less than 1, because 1 is our point. So we have x less than 1, we have x at 1. So that should be that the double derivative is 0. And then we also have x at greater than 1 that we need to check, okay? So let's look at the concavity if x is less than 1, right? So put it into our function. Let's say if we put 0, we're going to get a negative value. So we're concaving down, right? So our concavity, so our graph, concave down. And why is it concaving down? Is because if you sub in a value of x less than 1, right, into our double derivative, we're going to get a negative number. Okay, if we put x equals 1, we're going to get 0. So this is just the point of inflection. And then here, if we put in a value greater than 1, so let's say if I put 2, I'm going to get 12 minus 6 is going to be a positive number. So I'm getting concave up. Okay? So that means when we're sketching this, it would look around like that. And we have our point of inflection. And then we also have it concave up. Okay, so how does this function actually look like? So now you could take all the things we just learned and we can kind of figure out how we can draw this, right? Because we know our critical value, like we have above, are at -1 and 3, -1, and 3. And then we also have a point of inflection at x equals 1. So over here, we also have a point of inflection. Oops, that's a bad. So this is not an asymptote. I'm just going to make that clear. This is point of inflection. I'm just doing it dotted lines just so that you can see it, right? And so what do we know about this function? We know that it's an odd degree function, so that means it's going from one side to the other. It's a cubic function, right? The leading term, right? It's a cubic function, so that means it's going to go from opposite sides. It's going to go from one end to the other. Which end do we know? It's positive, so we're going from lower end to more positive, right? So that means we could start here. We know that we have a point of inflection here, and then we know that we can go down. So sorry, the point of inflection should be like that, and then we know that it's going down this, right? So let's say like that, and then we know it's going up again. Okay, so that's kind of how our function would look like. We know we pass this 0, we have a point of inflection at this point, and then we know we're going up. Oh, I missed that last part. Dang. That sucks. It's okay. So then we have something like that. That's how our function should look like. Okay? And that's essentially it. Now we've completed curve sketching. We kind of got an idea of how we can curve sketch now, right? So, yeah, so we kind of got that idea now. So one other thing is we actually don't know where this point of inflection is. We just know it's at x equals 1, but we don't know where on this line it is. So the way you could tell, though, is you can sub in the value, right, into the function. So x equals 1 into this function, and it will tell you where. So it's not exactly correct. So if we were to update that, so x equals 1 into the function, if we put 1 into the function, we'll get 1 minus 3 minus 9, right? So we'll get 1 minus 3, which is going to be -2. -2 minus 9 is just going to be -11. And then -11 plus 10 is still -1. So that means the point of inflection happens at -1. So it's actually a little bit lower. So I'm just going to erase this and make it a little bit lower. So it is going to go all the way down. It's going to happen right here. It's going to happen at -1. Okay? And that's essentially it. Other than that, let me see if I can remove this part. Yeah, I did. So it should be something like that. It should be at -1, right? The point of inflection is at 1, -1. Because all I did was just sub in 1 into the original function. Okay? And that's about it. That's essentially how you would do curve sketching at that point. Okay? All right, that's it for today. We're just doing concavity, and this is a bit shorter of a lesson, but we've covered everything in terms of curve sketching that you should be able to do on your assignment. If you have any questions, please let me know. Because of the holidays, it might take some time to reply back, but once we pass New Year's, I will be able to reply back to all the questions. Okay? Sounds good, and Happy New Year. Have a great break.